me just introduce Professor Adhikari first. He is, as far as I can make out, he's a mathematician by training, and he's interested in the quantum information processing and applications. So it's really true that all of these tasks are very much, they require mathematics pretty much, and computation as well. So Professor Adhikari has moved few places during his since 2012. He was first at IIT Jodhpur, then at BIT Mesra, and now he's at Delhi Technological University in the Department of Applied Mathematics. And today he's going to tell us about structural physical approximation of partial transposition. So Professor Adhikari, please take over.
Okay, thank you, ma'am. First of all, I would like to thank the organizer for inviting me to present here my work. So I would like to talk on this structural physical approximation of partial transposition. So this is a basic operation in quantum information theory. Partial transposition, we all know about this because it is the first operation that can detect the entangled state. So we will see that actually I am talking about this a structural physical approximation of partial transposition. So we will later see that what do we mean by this structural physical approximation of some positive map, but not a completely positive map. So I would like to start from here that in first few slides, I will recapitulate about the positive map and completely positive map. As in the introduction, Madam says that I am mathematician, so I will most of my talk I will use these mathematical concepts used in quantum information theory. So as you know that without mathematics, we cannot calculate, or we cannot do anything in physics. So physical concept is required, but simultaneously mathematics is also required. So so first of all, I will start with this positive map and then completely positive map, and then I will introduce this. What do we mean by structural physical approximation? Then after introducing this, we will see that what do we mean by structural physical approximation of partial transposition, and why we need structural physical approximation of partial transposition. So here we will see that a beautiful idea prescribed by Horodecki and Eckert, so that a partial transposition operation can be realized in experiment. Okay, so then I will talk about this structural physical approximation of partial transposition for 2-qubit system. So in this point we cover the 2-qubit system, that how SPAPT operation is applying has been applied on 2-qubit system, and then after doing this, we will go to the little bit complex structure that is 3-qubit system. So we will see that we can also apply this structural physical approximation of partial transposition on any one of the single qubit of a 3-qubit system. And then we will see that just by doing this, we can we are able to discriminate the different classes of 3-qubit system. Okay, so this is the structure of my talk. So let me start with the positive map and completely positive map. So first of all, let me define this. What do you mean by positive map? So it is a linear map lambda from the set of bounded operator in the Hilbert space HA to another bounded operator of the Hilbert space HB, and the map lambda is called positive if for all positive x that belongs to the this bounded operator on in the Hilbert space HA, the operator lambda x which belongs to this BHB is also positive. So lambda is said to be a positive operator if you take any element from BHA, and then the image of that element also gives you the positive element. So if for all, this holds for all positive x. So now, if you, in particular, if you take any density matrix, we know that the density matrix is a set of comes under this bounded operator, and its spectrum lies between from 0 to 1. So one can say that this this lambda is said to be positive if it takes every density matrix to another density matrix. Okay. So now, one example of positive map is this transposition map. So you know that when we use this transposition map, then its eigenvalues will not change. So this means that the density matrix, when we apply these transposition maps on any of the density matrix, so it's since it is a density matrix, so it is a positive semi-definite operator. So when we apply this transposition map on it, then it also gives a positive operator, that is a density matrix. So that means transposition map takes every density matrix to density matrix, another density matrix. So this means that it is a positive operator. So now the question one can ask this trivial question, that whether all positive maps applied to density matrix in the extended Hilbert space give density matrices or not. So this is obvious question, that if we applied any positive maps in extended Hilbert space, so that means if we would like to expand the dimension of the Hilbert space, so we can expand the dimension of the Hilbert space just by taking the tensor product of any density matrix with some identity operator. So this identity operator of any dimension from the dimensions start from 2, 3, 4, 5, 6, like this. So in general case, if we take any density matrix of order D, if you take any identity matrix of order D, and if we take the tensor product of that identity matrix with the density matrix, then it will become ID tensor density matrix rho. So if rho is the density matrix, then ID tensor rho. So it increases the dimension of the density matrix rho. So ID tensor D. So let us suppose if we have 2-qubit system. So this 2-qubit system is described by the 2 cross 2 density matrix. And if you take the identity operator in 2-dimensional space, that is I2, so then if you take the tensor product between I2 and the density operator rho, which is described by a 2 cross 2 2 cross 2 matrix, then I2 tensor this 2 cross 2 density matrix will give a 4 cross 4 density matrix. So 4 cross 4 matrix, not density matrix, 4 cross 4 matrix. So this means that the dimension of the matrix will change, is enhanced or it extends. Okay, so this means that if this happens, that means if the dimension of the resultant matrix is changing, then we expect that if we initiate from the density matrix, that means if we take any density operator rho, and if we take the tensor product of any order identity matrix, then whether it still represent a whether it is still represent a density matrix or not, this is a question. So this question we can pose in this way, that whether all positive maps apply to density matrix in the extended Hilbert space give also density matrices or not. So here, this question, to answer this question, we need the concept of completely positive map. So lambda, let us suppose this lambda be a positive map, and take any map ID, which takes the matrix MDC. So C is the set these elements of the entries of D cross D matrices are complex number. So all entries are complex number in general. So if we take this map from ID MDC to MDC, denote an identity map, then we say that lambda is completely positive if for all D, the extended map ID tensor lambda is positive. So here you should note this fact, that for all D, the extended map ID tensor lambda is also positive. If it happens, then we say that this mapping is a completely positive mapping, or this map is a completely positive map. So ID tensor lambda is a completely positive map for all positive lambda, for all positive map lambda, if it holds for all D, for all identity. Let us suppose if I2 tensor lambda is positive but I3 tensor lambda is not positive, then we cannot say that it is a completely positive. Okay, so if I2 tensor lambda, I3 tensor lambda, I4 tensor lambda, so if it remains positive for all D, then we say that this extended map is a completely positive map. So the example of this map is trace map. So it is a functional, and you can see that this trace map is a completely positive map. And you can easily verify that this trace map is a complete example of a completely positive map. So when we apply this ID tensor trace of something, trace of lambda, so ID of this, then that matrix trace map, so that ID tensor this lambda is let us suppose if it's some trace map, some density matrix rho, and if it gives some also density matrix, then ID tensor lambda is positive. So if you take this example trace map, it is a completely positive map. So now any completely positive map represent the most general transformation of quantum states. So you can, if you take any general transformation, you know that if rho is some rho described by some if the density operator rho is described sorry, if a quantum state is described by the density operator rho, then its evolution can be expressed by this completely positive map. So rho can be evolved like this, rho prime, rho goes to rho prime, and this rho prime can be written as ki rho ki dagger, where ki are the cross operator, and you can easily see that this transformation rho to rho prime, it represent this completely positive map. Now, why completely positive map is important? Because it is capable of describe an arbitrary quantum transmission channel. So if you go through this paper, Schumacher papers, so you can easily find out that these completely positive maps are capable to describe an arbitrary quantum transmission channel. And then this is also important because it transforms some unphysical operations such as quantum cloners and universal NOT gate, and that can be approximated optimally by an optimal CP map. So that means here also you can see that we are using this structural physical approximation, and this structural physical approximation is such type of operation which makes some unphysical transformation to physical one. So you can see later on that whenever we are applying this partial transposition operation, it is not a physical operation, okay, because this partial transposition operation is a positive map, but it is not a completely positive map. So if you would like to prove that it is not a completely positive map, then you can just take the identity operator of dimension 2. So that means if you take I2 tensor any transposition operation on some density matrix, then you can find that that the density matrix may not be a final density matrix, or at the output you may not get the density matrix. So so the transposition map, is a positive map, but it is not a completely positive map. So these positive but not completely positive maps are very useful in detecting the entangled state. Okay, so we can use this concept that if you are able to find out some positive map, and if it is not completely positive, then you can show that this type of maps can detect entangled state. Okay, so I have already told about this transposition map. It is a positive but not completely positive, because it is not too positive. Too positive means you can take I2 tensor lambda, it is not a positive for this transposition map. So now here you can see that a density matrix of a bipartite system. This is the first separability criteria given by Perez and Hordecki. So it states that a density matrix of a bipartite system is inseparable if and only if there exists a positive map acting on a subsystem such that the image of the density matrix is not positive definite. So if you understood this partial transposition operation, then you can see that if you apply this transposition map on one of the subsystem, then the resulting the composite system may not give the positive eigenvalues. And since you are applying the transposition map on one of the subsystem, and this makes the composite system this makes the composite system does not represent a quantum state. So this happens only for the entangled state and not for the separable state. So this this transposition operation may act as a entanglement may serve as an entanglement detection tool. So we can use this parcel transposition operation to detect entangled state. So here you can see that the parcel transposition map can be defined in this way. If you have two system A and B, two subsystem A and B, so the total subsystem, total composite system, when we apply this operation IA tensor TB on the total composite system, then the total composite system may not represent a physical state. After applying this map, then we can say that the state on which we are applying this type of operation, that state may not be a separable state, it may be entangled state. So this type of observation was observed by Asher Perez in 1996, and then this idea was developed by Hordakis. Now, structural physical approximation, what do we mean by this? So let me speak something about this. So we talked about this positive map and not a completely positive map. So whenever we have a map which is positive but not a completely positive, so you can see from here that this completely positive map represent the most general transformation of quantum states. Okay, so that means if you apply the completely positive map, so this means completely positive map on some quantum state, then it also gives some quantum state. Okay, so it is the most general transformation. So from this point it is clear that if you are taking some map which is positive but not completely positive, so this means that it may not give the density matrix at the output. Okay, so this means that this type of map which is positive but not completely positive map, it is not possible to implement this in a lab. So this means that this operation which is positive but not completely positive, this operation is not a physical operation, and since it is not a physical operation, so we cannot apply it in the we cannot implement it in the laboratory. So how to overcome this difficulty? So to overcome this type of difficulty, Hordaki and Eckert suggested a way to approximate, if we approximate this type of unphysical map in such a way so that it will become a physical map. Okay, so their idea is very beautiful, and they have approximated this type of unphysical map to such that it will become a physical map. So this type of approximation is known as structural physical approximation. So you may have some queries about this structural physical approximation. Why we name this type of thing structural physical approximation? First of all, we are doing approximation. We are approximate some positive but not completely positive map. That is why this approximation word come. What is physical? Why physical? Physical means that when we approximate this positive but not a completely positive map, then the map will become a completely positive map. So since the map will become completely positive after approximation, so we can say that this is a physical approximation. So this means that we can map in unphysical, we can approximate an unphysical map to a physical map. Okay, so that is why physical word comes. And then why structural? What does this mean? So the term structural comes from this fact that whenever we take a suitable proportion of depolarization map and which mixes with the positive but not completely positive map, then it modifies the structure of the original map. Okay, so structure here, structural means that the idea is that we have to mix the unphysical map with the depolarization map. Okay, so depolarization maps means that when we apply this depolarization map on any quantum state, so it reduces to the identity map. Means depolarization map makes the transformation which takes the density matrix to the identity matrix. And you know that the identity matrix is nothing but the maximally mixed state. So that means if we mix sufficient proportion of this depolarization map with this positive but not completely positive map, then it may approximate this positive but not completely positive map, and then it modify it. But with this mixture, it does not modify the structure of the original map. Okay, so what does this mean? It does not modify the structure of the original map lambda. Okay, so our original map was lambda. It is a positive map, but it is not a completely positive map. So when we mix some depolarization map with this lambda, then it we are approximating something. So we are approximating this lambda, which is positive but not completely positive. But just mixing this does not modify the structure of the map lambda. Okay, what does this mean? This means that the direction of the generalized block vector before and after the application of this map is same. So, so that means when we are applying this map on any vector, it does not modify the structure of the vector, means that it does not change the direction of the vector. Okay, so that means before application of this approximation, the direction of the block vector is same after the application also. Okay, so that means the direction of the block vector will remain same after and before the application of this approximation. Okay, so what 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 means this means what approximated we have, it direction doesn't change. So what change, what approximated, so that it will become a unphysical, it will become a physical map from the unphysical map. It changes the length of the vector. Okay, so whenever we are approximating any positive but not completely positive map, that this means that we are not changing the direction of the vector, but we are changing the modulus of the vector. So that means its modulus may decrease, may increase, right? So it does not modify the structure of original map. Simply means that it doesn't change the direction of the block vector, but the magnitude of the block vector may change because of this approximation.
Can I ask a question?
Yes.
Yeah, actually, so we think about block sphere to be a unit sphere, and this block vector will have unit magnitude. So what does it mean to talk about length of the vector changing? Magnitude?
You know that the block vector, if all the states lying on the surface of the sphere, so that means they are pure states. Okay,
That's right. So
and
it can
the
become
state
from
which
pure
is,
to mixed state?
yes,
I see.
yes. So that means its mixedness increases,
I see.
because we are applying this depolarization map with the positive map. So
I
when we are
see.
applying this depolarization map with the positive maps, that means depolarization maps takes the density matrix to the identity matrix. So identity matrix is the maximally mixed state. So
That's right.
it is in the middle of the sphere. Okay,
Huh.
so that means the magnitude of the vectors decreases, right?
So only way it can
Eventually,
change is decrease.
yes,
Yes.
yes, yes,
Okay.
yes.
Okay. Thanks.
So this increases the mixedness of the state. Okay,
Uh-huh.
so this is this is the thing. So this is the approximation. So in this way, we can apply the structural physical approximation. So now, what is the? Let me recapitulate the characteristic of the structural physical approximation. So it tells us that it is an approximation, it is a transformation, and it takes any positive map to completely positive map. Okay, so that means this approximation bring any positive map to the completely positive map. Now, SPA has been exploited to approximate unphysical operations such as parcel transpose operation. So you know that parcel transposition is not a physical operation because when it applies to some for some density matrix, the if the state is entangled, then it may not be a density matrix after the application of the parcel transposition map. So this means that this operation is positive but not completely positive, and hence it is an unphysical operation. But we can apply this structural physical approximation on parcel transposition map to make it from unphysical to physical one. So now what is the idea? So as we have discussed this thing, that the idea is to form a mixture of the positive map P with a completely positive map O that transform all quantum state onto maximally mixed state. So idea is that we have to bring any positive map, any state, all quantum state you can consider, and whenever we are applying this type of approximation, then it bring all the quantum state to the maximally mixed state. So that means it tends towards the maximally mixed state. So so that means we are making this unphysical operation to physical one. We are doing this not complete. We are going from not completely positive map to the completely positive map. So since we are making this completely positive map, so that means it can now be implemented in experiment to detect the entanglement directly without full state tomography. But here you should note one fact, that whenever we are doing this, we need some prior information about the state. So without any prior information, you cannot apply this structural physical approximation. So now, so this structural physical approximation of parcel transposition operation. So now we are considering a particular type of positive map, and that is parcel transposition operation. And we are applying this structural physical approximation on parcel transposition map. So as you know that parcel transposition operation does not represent a completely positive map, and thus it cannot be implemented in real experimental setup. So we need to approximate it so that we can get rid of it and we can implement it in the real experiment. So this type of approximation is known as structural physical approximation of a parcel transposition map. Now, how to construct this structural physical approximation of parcel transposition map? So to do this, let us consider a bipartite system, and it is described by this density operator rho AB. So you know that the parcel transposition operation is defined like this. So it takes the density operator rho AB to this image, that is I tensor TB operating on rho AB. So now the idea is that we have to add appropriate proportion of I tensor TB with a depolarizing map, and with this addition, it may transform any density matrix onto a maximally mixed state. So since the state density matrix tend towards the maximally mixed state, so this means that this construction provides us a completely positive map. The reason is that the positive. So here you can see that we are when we are applying this map on any density matrix, then the density matrix goes towards the maximally mixed state. So why? What is the reason behind this? The reason is that the positive eigenvalues of maximally mixed state generated by the depolarizing map may dominate the lowest negative eigenvalues generated by the induced matrix. So what we would like to do here, that I tensor TB. So this operation is a positive but not completely positive map. So what we need to do, we just make this transformation I tensor TB, we have to make this transformation as a completely positive transformation. So we need to transform this, we need to approximate this map as a completely positive map. So what we will do here, so we know that whenever we are applying this I tensor TB on any entangled state, then if the state is entangled, that means we are applying this map on any entangled state, so it gives a negative eigenvalue. Okay, so if it is a 2 cross 2 system, then it gives you the one eigenvalue negative. If it is m cross n dimensional system, then the number of negative eigenvalues will be m minus 1 into n minus 1. Okay, so that means you know that there are negative eigenvalues when this transformation I tensor TB operating on any entangled state rho AB. So there may be, when you are increasing the dimension of the system, there may be more than one eigenvalue. So what you have to do, you just have to take the minimum most eigenvalue. Okay, so if you concentrate on the minimum most eigenvalue, and if you add the depolarizing map, so that this minimum most eigenvalue, if we are able to make this minimum most eigenvalue positive, just by mixing this depolarizing map, if we make our transformation, if we mix our transformation with the depolarizing map in such a way, so that it makes the most negative eigenvalue positive, then we can say that all other eigenvalues will be positive also, because we are making minimum most eigenvalue positive, so all other eigenvalue will be positive automatically. So this idea makes the transformation positive. Okay, so since we are taking this induced map, which is I tensor I tensor I tensor TB, so just recall the completely positive map. So a map is said to be completely positive, a map lambda is said to be completely positive if ID tensor lambda is positive for all D. So this is the definition of the completely positive map. So here we would like to show that I tensor TB is a positive map. So completely, if you show that this is completely positive, then automatically it will become a positive map. So to do this, what we will do, we just take this I tensor TB with the tensor product of I tensor I, and if it is positive, if this induced map is positive, then we can say that this I tensor TB will become positive. Okay, so it is a completely positive, it will be completely positive, and then I tensor TB is positive. So this is the idea, that we have to consider this induced map and show that the lambda minimum of this induced map should be positive. Okay, so this is our task, to make the minimum eigenvalue of this induced map positive. We have to make it. So how to make it? We have to make this minimum most eigenvalue positive if we add sufficient proportion of depolarizing map. Okay, so let me start with this one. So let me now tell you step by step. So first of all, let me just concentrate on this induced map, which is I tensor I tensor I tensor TB, and it operates on the maximally entangled state in the corresponding system, composite system. So if you are considering the 2 cross 2 system, 2 tensor 2 system, then the maximally entangled state is 1 by root 2, 1 by root 2, 0, 0 plus 1, 1. So if this induced map applying on this psi, then it will give you the negative most eigenvalue minus lambda psi. It is the negative most eigenvalue. Well, lambda is positive, so minus lambda is the minimum most eigenvalue. So if this is the minimum most eigenvalue corresponding to this eigenvector, and if we are able to make this minimum eigenvalue positive just by mixing the appropriate proportion of depolarizing map, then we can say that this map I tensor I tensor I tensor TB is completely positive. So our task is to make it completely positive. So to do this, we have to first define some map, and then we will show that this map is completely positive. So here the I tensor TB tilde tilde, we denote this as a approximation of I tensor TB. Okay, so the approximation map I tensor TB is denoted by I tensor TB tilde. So when this map acting on this rho AB, a two qubit uh, bipartite system. So after the application of this I tensor TB tilde on rho AB, it gives us some probability of getting this maximally mixed state, that is I tensor I by d square. So this means that it is the d-dimensional identity we are talking about here, d tensor d system. So in the d tensor d system, the maximally mixed state is represented by I by d and I by d. So it will be I by d tensor I by d. So it is I tensor d by d square, and we are taking the p proportion of it. P is the probability of getting this maximally mixed state, and 1 minus p is the I tensor TB when operating on rho AB. So here you can see that I tensor TB when operating on rho AB, it gives you the negative eigenvalue if the state rho AB is an entangled state. So if the state rho AB is an entangled state, then I tensor TB when operating on rho AB gives you the eigenvalue, negative eigenvalue. So we will concentrate on the most negative eigenvalue, and just taking this proportion, p proportion of the maximally mixed state, and the 1 minus p proportion of this. So what would be the p proportion, so that the it makes the minimum most eigenvalue positive. So that proportion of p will work, and that gives all the eigenvalues of I tensor TB tilde positive. Okay, so idea is this one, that we have to make the eigenvalue of I tensor TB tilde, we have to make the proportion in such a way so that the all eigenvalues of I tensor TB will become positive. So to do this, what we have to do, we need to this map I tensor TB tilde is positive, and we can show this only when we show that I tensor TB tilde is positive. Okay, so the induced map is positive. If this induced map is positive, then we can say that this map is also positive map. So to do this, we will use this Wiles inequality, and it says that if A and B are Hermitian operator, then lambda minimum of A plus B greater equal to lambda minimum of A plus lambda minimum of B. So we can exploit this Wiles inequality to prove this fact. So now consider the minimum eigenvalue of I tensor TB tilde. So when you find out the minimum eigenvalue of this induced map just by using this Weil inequality, we can get this thing. So you can see that when we are considering the D tensor D system, and for that system the minimum eigenvalue of this induced map is greater equal to this one. So you can see that we can find out suitable P so that this term will be positive. So if this term will be positive, then lambda minimum of this operator, the lambda minimum of this induced operator is greater or equal to 0. So if minimum most eigenvalue, so minimum eigenvalue is greater or equal to 0, means all other eigenvalue will be equal to 0, and then we can say that this induced map is positive, and hence I tensor TB tilde is positive. So the induced map, this I tensor TB tilde is positive when P is greater or equal to 0. Just by simplifying this, you can see that just make this term positive, so you can arrive at this. So if P is greater or equal to lambda d to the power 4 by 1 plus lambda d to the power 4. So here you can consider P is greater or equal to this, so the minimum proportion P will be equals to lambda d to the power 4 by 1 plus lambda d to the power 4. So it is sufficient to consider this minimum value of P to make this minimum eigenvalue of induced map positive. So then the minimum eigenvalue of I tensor TB tilde is given by this one, lambda minimum of, so you can just apply this one. So in this case, if you apply this lambda minimum of I tensor TB tilde and using Wiles inequality, we can arrive at this relation, this inequality. So lambda minimum I tensor TB tilde rho AB is greater or equal to P minimum of 1 by D square plus 1 minus P minimum of lambda minimum of I tensor TB rho AB. Okay. So now, if this state rho AB is separable, so now consider this fact. So now we are considering that one more thing you have to understand here, that whenever we are applying the partial transposition operation on any state, so the negative eigenvalue is the signature of the entanglement. So if you are getting the negative eigenvalue of I tensor TB, then you can say that this state is entangled. But here after approximating this I tensor TB, we arrive at some approximation, we arrive at some state and whose all eigenvalues are positive. Okay, so now the question is that if we perform this approximation operation, and if we are getting all eigenvalues of the resulting density matrix is positive, then how we can detect the entanglement? So what would be the criteria for the detection of entanglement when this type of approximation has been applied? Okay, so that's why we come to this point, that if this state rho AB is separable, so if this state rho AB is separable, so the minimum eigenvalue when you applying this I tensor TB on rho AB, and the minimum eigenvalue will always be positive, because we are considering rho AB is a separable state. So since it is separable, so this term will be greater or equal to 0. So 1 minus P minimum lambda minimum I tensor TB is greater or equal to 0. So this always gives you positive. So that means the addition of these two terms, this addition of these two terms is greater or equal to, definitely greater or equal to P minimum into 1 by D square. So we make this term is greater or equal to 0, and this term will be positive only when rho AB is separable. So here we have arrived at the separability condition, that the minimum eigenvalue of the approximation map, will be greater or equal to P minimum by D square whenever this rho AB is separable. If this inequality is violating, then we can say that this state is entangled. So I tensor TB, the approximation, the minimum eigenvalue of the approximation are all positive, but it has some critical value. And if the minimum eigenvalue is going beyond that critical value, then we can say that this state is separable. If we have some state for which the minimum eigenvalue of this approximation is less than this critical value, then we can say that this state is entangled. So you can see that this value is always positive. So since this value is always positive, so it's always all eigenvalues are positive, and here we are getting some critical value of the minimum eigenvalue of the I tensor TB tilde, so that we can have this separability criteria. So here P minimum, you can just put this P minimum lambda d to the power 4 by 1 plus lambda d to the power 4 here, and then you can have this condition, this critical value. Okay, so this means that for D tensor D system, bipartite system, if the minimum eigenvalue of this approximation map is greater equal to this quantity, this critical value, then we can say that this state is separable. Violating this criteria, violating this inequality gives this state this is the indication of the entangled state. So now let me talk about this SPAPT of 2-qubit system. So in this, you can consider any general 2-qubit system is given by this rho 1, 2. And then we can make this structural physical approximation of rho 1, 2, and it gives rho 1, 2 tilde is 1 by 3 I tensor T tilde plus 2 by 3 theta tilde tensor D tilde. So here you may note here that we have approximated this partial transposition operation in this way, but the problem is that here we still have this I tensor TB rho AB. So how to get rid of this term? So that means approximation include this term I tensor TB. So again, this approximation if may not the experimentalist may not be able to apply this operation. Okay, so what we will do, we have to we have to approximate, or the approximation may be given in such a way, in such a form, so that experimentalist can use it comfortably. Okay, so to do this, they have to use the local operation and measurement strategy. Okay, so prepare and measurement strategy, if you take, then you can write these you can write this operation. Sorry. You can write this operation in this way. Okay, sorry. In this way. So I tensor T tilde. So here T tilde is the structural approximation of the transposition map. Theta tilde is the structural approximation of the inversion map. And D tilde gives you the depolarization map, approximation of the depolarization map. And they can be applied in this way, where sigma I is the Pauli matrices. So here you can see that T tilde rho is given by summation k equals to 1 to 4 trace of mk rho vk. Here vk are the basis in the two-dimensional Hilbert space, four-dimensional Hilbert space, and mk rho you can see that half vk star. So this is a measurement operator, and using this measurement operator, you can easily implement this transposition map in the laboratory. So just by using this concept of this I tensor T tilde, means structural physical approximation of T, structural physical approximation of theta, that is the inversion map, and D is the depolarization map. So if you take the structural physical approximation of this map and with suitable proportion 1/3 and 2/3, then you can implement this this operation rho 1 to tilde. And this rho 1 to tilde can be obtained experimentally. So here we have calculated explicitly the matrix elements of rho 1 to tilde, and they are described in this form. They can be given in this form. So now the properties of rho 1 to tilde, we know that rho 1 to tilde is the structural physical approximation of rho 1 to. So it is all its eigenvalues are positive. So that means it is a positive semi-definite matrix. And then trace of rho 1 to tilde, if you carefully look at it, then you will get trace of rho 1 to tilde is equals to 1. It is a Hermitian matrix, and this means that rho 1 to satisfies all the properties of the density matrix. So now the question is that the critical bound on minimum eigenvalue of rho 1 to tilde determine whether the state rho 1 2 is entangled or not. So here we have already seen that the entanglement criteria is given in terms of the minimum eigenvalue. So there are literature in the literature you can find that the minimum eigenvalue can be calculated experimentally. But here we can find out the minimum eigenvalue with some different approach, just by the approach of witness operator. So we can construct the witness operator, and then we can calculate the minimum eigenvalue of rho 1 to tilde. So to do this, what we have to do, so to construct the witness operator, let us start with this operator rho 1 to tilde. So here, we are considering the operator O, which is given by rho 1 to tilde minus 1/9 rho 1 to T2. Okay, so then after some calculation, you can find the expectation of this operator O with respect to this state phi, and the phi is the non-maximally entangled state in the four-dimensional Hilbert space. So then the expectation value, if you calculate, then you can find out this one. This calculation is 2/9. So here you can see that rho 1 to tilde minus 1/9 rho 1 to T2 phi equals to 2/9. So 2/9 comes from this fact that this one. So when you are calculating this value, so lambda value can be calculated for 2 cross 2 system, 2 tensor 2 system, it comes out to be 1/2. So if you put here lambda equals to 1/2, D means 4, 2 tensor 2 system. So you can put here D equals to 2. So so if you calculate this, then you can have this minimum value also, p minimum. So if you calculate this p minimum, lambda equals to 1 by 2, and then 2 to the power 4, so it will be 2 cube, and then you can get here 8 by 9. So one is 1 by 9, another is 8 by 9, and if you calculate this portion, then you can see that for 2 cross 2 system, so lambda minimum I tensor TB tilde is greater or equal to 2 by 9. So calculating this, so we can have this W opt rho 1 to T2 can be written as W opt, and then max witness operator, this witness operator can be given by 1 by 955 T2. T2 is the this transposition operation. So the optimal witness operator can be written in this form. So the trace W opt rho 1 2 gives you lambda minimum minus 2 by 9. So since this witness operator, just by using the characteristic of the witness operator, we know that for all separable state rho 1 2, trace W opt rho 1 2 should be greater or equal to 0, and there exists at least one entangled state for which trace W opt rho 1 2 is less than 0. So just for separable state, we have this condition: trace W opt rho 1 2 is greater or equal to 0, so lambda minimum is greater or equal to 2 by 9. Okay. So this value, if we have lambda minimum less than 2 by 9, then we can say that this state is entangled for tensor 2 system. So now the condition is that you can see here W opt, here we are using this W opt. So W opt is this 1 by 955 T2. So partial transposition operation, again we have used it here. So we cannot implement it in the experiment. So we can just write down theoretically this 55T2, and then we can express it in terms of the Pauli matrices, and then only you can say that W opt can be implemented in the experiment. But here we are doing the different thing. We can approximate this partial transposition operator, and then we can write this another operator which is given in this form 55 minus 2 by 9 I. So we can construct this operator, and this construction comes from this trace W of rho 1 2. So just by manipulating a few steps, you can reach here this trace 55 minus 2 by 9 I rho 1 2 tilde, and we can consider this operator 55 minus 2 by 9 I as V, and then you can see that trace V rho 1 2 tilde is less than 0, and this means that this operator detect the entangled state described by this approximation rho 1 2 tilde. So now you can have these properties of the operator V. Since I don't have much time, so let me proceed from here. And the main thing is that we have again approximated this operator V, and then we have shown that just by using two measurement, we can find out the value of trace V rho 1 2 tilde. From the heading, you can see that trace V rho 1 2 tilde gives you the minimum eigenvalue of rho 1 2 tilde. Okay, so trace V rho 1 2 tilde, since trace V rho 1 2 tilde gives the minimum eigenvalue of rho 1 2 tilde, so minimum eigenvalue of rho 1 2 tilde is responsible for the detection of entanglement. So experimentally we can detect the minimum eigenvalue just by using the witness operator. Now the question is how much measurements we need to determine this trace V rho 1 2 tilde. So one can easily show that the number of measurements needed to determine the value of trace V rho 1 2 tilde is only 2. Okay, so time is less, so I am skipping this one. So you can go through my paper, this physical review a paper. So maybe it is given here. Yes, so you can see this paper, and you can find out the details of these calculations and details of the logic what I am giving you here. So now let's come to the 3-qubit system. Let me talk about this 3-qubit system. So here also we are applying this structural physical approximation of partial transposition on 3-qubit system. So since we have 3-qubit system, so if you apply the partial transposition operation on 1 qubit, and if you find its negative eigenvalue, the resulting after the operation, if you find that the system gives negative eigenvalue, then you can say that the state is entangled. The same thing we can apply here, and then we can apply the partial transposition operation, structural physical approximation of partial transposition, and we have defined this in this way. So structural physical approximation when applying on 3-qubit system, this is the transformation is defined in this way. Okay, so so you can consult this paper in EPJD. So you can find out the detailed calculation there. So the main idea is that we are approximating this partial transposition in for the 3-qubit system, and the transformation is given in this form, and then we have calculated this appropriate proportion of PA. So that means here also we are adding this appropriate proportion of maximally mixed state to the this positive but not completely positive map, and this appropriate proportion makes the negative most eigenvalue of this operation T tensor I tensor I make this negative most eigenvalue positive just by using this appropriate proportion PA. So now to find out the appropriate proportion, we will use on again the Wiles inequality, and then just by calculating a little bit, so we arrived at that this lambda minimum rho T tilde is greater equal to PA by 8, and we have used this condition that whenever T tensor, whenever the transposition operation applying on the first qubit, then rho ABC, the 3-qubit system, gives you the positive eigenvalue, and it happens only for the separable state. So when this for all separable state it should happen. So T tensor I tensor rho AB rho ABC should give you the positive eigenvalue for all separable state. So again we are using the same concept and find out the minimum eigenvalue of the approximated map is greater equal to PA by 8. So now the question is that how to find out this PA. This is the separability criteria. So the equation 30 gives you the separability criteria for the 3-qubit system in terms of the structural physical approximation. But now the question is how to find out PA. So the minimum value of PA can be found out that this approximated map, when this approximated map will be completely positive. So when this approximated map will be completely positive, this determines the value of minimum value of PA, and this minimum value of PA gives you the critical bound on minimum eigenvalue of the approximated map. So we can find out that this approximated map T tensor I tensor T tilde is completely positive whenever PA, this proportion is greater equal to 4 by 5. Okay, so if PA is greater equal to 4 by 5, then this map approximated map will be completely positive. So here we have shown you that whenever the partial transposition operation applying, whenever this operation is applying on the first qubit, it may apply on second qubit, it may apply on third qubit also. So in every case, you can get that the proportion will be greater equal to 4 by 5. You can check it. So now here we are discussing few results that provide us the necessary condition for the separability of a 3-qubit system. So here you can see that the conditions are separable, conditions are necessary but not sufficient condition. So this first theorem states that if the state described by the density operator rho ABC denoting either either a separable state of the form ABC or a biseparable form ABC, then the inequality following inequality is satisfied. So the minimum eigenvalue of the approximated map is greater equal to 1 by 10, then you can say that the state is either separable or biseparable of this form ABC cut. So in this cut, the state is biseparable. So similar way, you can find out that lambda minimum rho B tilde is greater equal to 1 by 10. So this critical value 1 by 10 comes from this fact. So you can just put here the minimum value of PA. So minimum value of PA will be this 4 by 5. So if you put here 4 by 5, then you can get that 1 by 10. So minimum eigenvalue of the approximated map will be greater or equal to 1 by 10, and which is the separability criteria. But this condition is necessary but not sufficient. So same thing you can see for in theorem 2, that if the state is of the if the state are separable, that is fully separable state, or the biseparable state, or of the form this BAC, then minimum eigenvalue of the approximated map is greater or equal to 1 by 10, and this for lambda minimum rho TC. So now how to
Professor
classify these
Adhikari,
three? Yes,
can
ma'am.
I interrupt?
Just
It's almost time. So could you please just some wind up and summarize the results?
yes, I am just.
201.
I will take
Yeah,
just 2 minutes.
sure.
2 minutes
Okay.
just.
Okay, that should be okay. Thanks.
So we can classify the three qubit system just by using this result. So if you have this lambda minimum rho tilde is less than 1 by 10, then rho ABC is a genuine entangled state. If lambda minimum rho TA tilde is greater or equal to 1 by 10, and either this condition lambda minimum rho TB tilde is less than 1 by 10, or TC less than 1 by 10, or TB less, both less than 10, then rho ABC is biseparable in ABC curve. So in this way we have BAC curve and the result for other curves and result for fully separable state. Thank you. Thank
Okay.
you, ma'am.
So yeah, thanks a lot for this very clear talk, and let's have some questions if there are any. Uh, I don't see any in the chat box. Participants, please raise your hands if you have any questions. I don't see any. I don't see any. So perhaps if you have questions later on, please feel free to write to Professor Adhikari. I'm sure you will get your responses. Thank you very much, Professor Adhikari, once again.
Thank you. Thank you, ma'am.
Thanks. Let's now move on to the